Hey guys, welcome to Unit 12, Notes B. Today we're going to study how to balance redox reactions. Balancing redox reactions is not as straightforward as balancing non-redox reactions because we also have to keep track of the oxidation numbers to make sure that the electrons are equal on either side of the reaction. So we're going to look at two different methods that you can use to balance redox reaction. The first is called the change in oxidation number method, and the second is called the half reaction method. You do need to know how to do both of these methods. So first, the change in oxidation number is based on this principle that the total oxidation number increase must equal the total oxidation number decrease. We already know how to do a couple of these steps, these first couple of steps. When we write the equation, we go through and we assign the oxidation number for every single element based on following the rules for each compound. Then we're going to determine which element is oxidized and which element is reduced, using the concept that oxidation is loss, so I'd be looking for the loss of electrons or an increase in oxidation number, and reduction is gain, so I'd be looking for a gain of electrons or a decrease in oxidation number. Once I find that pair, I'm going to connect the atoms that change using a bracket. And in the middle of the bracket, I'm going to write what the change in oxidation number was. My goal is then to create equal changes. So for example, if I have a gain of 4 but a loss of 2, then I would need to double that loss in order for it to balance out with a gain of 4. Once we have the proper multipliers, we're going to use those as coefficients on the connected atoms. But then you may also need to, at the end, go back to the things that weren't part of that redox reaction and also balance them. Old school, by inspection, by looking and counting the number of atoms. So let's try one. First thing I want to do to this equation is go through and write my oxidation numbers. So my sulfur is 0. With hydrogen I have +1 and the oxygen's -2. So +1 and -6, and I want that to be neutral. So that nitrogen's going to need to be a +5. Onto the sulfur dioxide, oxygen's -2 twice would make the sulfur a +4. If oxygen's -2, nitrogen would have to be +2. And then we have +1 and -2 for our water. Now I want to find out what is changing. So let's start with the sulfur and connect it from its initial oxidation state of 0 to its final oxidation state of +4. That's going to be an increase of 4. The hydrogen's the same on each side, but when we get to the nitrogen, I find my other change. Going from +5 to -2, from 5 down to 2, is a decrease of 3. So my oxidation number has increased by 4, but decreased by 3. We want that to be equal. So it's kind of like finding the lowest common multiple. What could I get 4 and 3 to each become that would be the same? For the 4, I'm going to need to multiply by 3, whereas the 3, I would need to multiply by 4. That's going to allow my increase to be 12 and my decrease to be 12. So I can find a matching number. So if I need 4 times the change in oxidation numbers, if I need 3 times this change in oxidation number, that means I need 3 of these sulfur atoms. So we're going to put a 3 coefficient in front of the substances that are connected to the bracket where I multiplied by 3. Then in the bracket where I'm multiplying by 4, I need 4 times the change in oxidation number. So that means I need 4 of those nitrogen atoms on either side. If each nitrogen has a change of 3, if I have that happen 4 times, I get a total change of 12. And if each sulfur has a change of 4, if I have that happen 3 times, I get the change in 12. And only then will they be equal. Don't forget the very last step, which is that I want to find out how many water atoms I need. And for that, I need to balance my hydrogens and oxygens from this side. So I can see here I have 4 hydrogens, so that would need 2 water molecules. And if you count up the oxygens, that will also work out for balancing the oxygens as well. So this would be our first example, balancing by the change in oxidation number method. You start off by identifying all of your oxidation numbers. Then you do your brackets, where you're showing the gain and the loss in the oxidation number, or the increase and the decrease, I should say, in the oxidation number. Then you find your multiplier and apply that multiplier to each connected molecule. So on the top, multiplier of 3 applied to the sulfur molecules, whereas the multiplier of 4 applies to the nitrogen molecules. And then we can't forget about this little water over here. Make sure that the entire equation is balanced. Now, if a reaction specifically says that if a reaction specifically occurs, so if the problem specifically says that it occurs in an acidic solution, then you have water and hydrogen ions, hydroxide ions, all present in an aqueous solution. So if we want our answer to be an acidic solution, there's a strategy to this. What you're going to do is you're going to look at your reactants and your products, and you're going to add water molecules to the side that is lacking oxygen. This is the only way that you're going to be able to balance the oxygens, is by adding water to the side that is lacking oxygen or that has less oxygen. Whenever you add water to one side, you're going to add hydrogen to the other side in order to now balance the hydrogen atoms that we've introduced. It is also okay to just add hydrogens if needed, but whenever you add water, you are going to have to add the hydrogens. The water goes to the side with less oxygen, and then the hydrogen ions to the other side. So say, for example, we added water to the reactants, the hydrogen ions would go on the product side. If you want to make it a basic solution, you're going to go through those same exact steps. Fix your oxygen, fix your hydrogen, but then we don't want to leave it as a hydrogen ion because that would make it acidic. So how do I neutralize that acidic solution? I need to add hydroxide. And you add as much hydroxides as you have hydrogens so that they cancel out. That's then going to usually create water on both sides of the equation that you have to watch out for. And then on the other side, you're also going to add hydroxide. We want our solution to end up being basic. So water to the side with less oxygen, hydrogen to the other side, and then if and only if it's basic, hydroxides to both sides. But then we want to make sure we watch out for the water canceling. So let's walk through an example where we're doing something like this. It's going to start off the same. I'm going to start off by determining my coefficients using the change in oxidation number method. So my chlorine, the chloride ion here, the oxygen having -2, 4 of them for -8, but I want a -1 left over, so the chlorine will be +7. The ions each have an oxidation state of -1, and then in its single state, standing state here, this I2 would have an oxidation state of 0. So my change is between the chlorine and between the iodine. So going from +7 all the way down to 0 and then another -1 is a change of 8, whereas going from -1 up to 0 would be a change of +1. So wherever the oxidation number is decreasing is always my reduction, as I'm gaining electrons, and the oxidation would be the +1. So now I want to make these the same. How can I get 1 and 8 to be the same? I need a multiplier here. Let me use a different color. So I'm going to multiply 1 by 8 in order to get the oxidation change to be the same, meaning that I need 8 times the iodide atoms. So I'm going to put an 8 here, but would you put an 8 over here as well? Would this ever balance? 8 single iodine ions and 8 diatomic iodine molecules. That does not make sense. You would actually just use a 4 over there because we want a total of 8 iodine atoms, and since they come in pairs on the product side, we only need 4. So this is telling you how many atoms we need of the thing that has this change. So this is going to balance my atoms or molecules or substances that are involved in the redox reaction. But notice how I have an oxygen here with no oxygen on the rest of the molecules. So let me clean up some of our redox work. Keeping in mind that we just determined there are 8 iodide ions and 4 iodide molecules. I'm going to start by adding water to fix my oxygen problem. The oxygens are on the reactant side, so it's my product side that's missing oxygens. So I'm going to add water. I have 4 oxygen atoms, so I need 4 oxygen atoms on this side. That now creates 8 hydrogen ions, or hydrogen atoms. So I need hydrogen, which will be in the ion form on the reactant side, and I want to balance that by showing there's 8 of them. Now I have 8 hydrogens on either side. I have a chlorine on each side, 4 oxygens on either side, and 8 iodines on either side. So my atoms are balanced, and then because I did my change in oxidation number method, I also know my electrons are equal. So this is balancing in an acidic solution in order to use the change in oxidation number method. All right. Again, same kind of steps. Oxidation numbers first. Do your change in oxidation number, find your multiplier and apply it. And now we also talked about be careful when you have subscripts that affects how many multipliers you need. And then you use your water and hydrogen to balance the rest of the atoms. This is because it's in an aqueous solution, and so we can bring in the hydrogen and the hydroxide and the water as needed. All right, so let's say we have this now balanced acidic solution, and we want to make it a basic solution. So let me use blue for basic. It's these hydrogen ions that make it acidic. So in order to make it neutralize, in order to cancel out the acidic, I'm going to add 8 hydroxide ions. And that 8 hydrogen and 8 hydroxide are going to combine to form 8 water molecules. Now that I know how many hydroxide ions, or I meant to underline, how many hydroxide ions I have, I'm going to add that same number of hydroxide ions on the other side. This is what's going to end up making this a basic solution. Now, we do have to watch out for the water canceling, remember. So my hydrogens and hydroxides combine to form water. There's 8 waters now on the reactant side, but there was already 4 waters on the product side. So we're going to cancel mole for mole, meaning 4 of the water molecules will cancel out, so all of the ones on the product side, and 4 of the 8, leaving 4, would cancel on the reactant side. So I could rewrite this as 4 H2O reacts with, and this part is going to remain the same, the ClO4 minus the 8I minus, forming the chlorine ion and the 4 iodides. And then the water's gone now. I just have those 8 hydroxide ions. And this would be our final answer in a basic solution. Notice how I started with the acidic answer. So no matter what, you're going to be using water and hydrogen to balance the molecules in the first place. And then you can add hydroxide in if we need to change the acidic solution into the basic solution. All right. So we had our acidic solution. Based on the number of hydrogen ions, I add that many hydroxide ions to both sides. I combine the hydrogen and hydroxide to form water, but then I cancel out or reduce down the water so it's simplified to how much net water. So we use the water to fix the oxygens, then the hydrogens, and then the hydroxide to make it basic. All right, let's move on to the other method, something called the half reaction method. This is going to separate or pull apart your 2 reactions, the oxidation reaction and the reduction reaction, and have you focus on each reaction separately, balancing each reaction separately, and then putting them back together. So we're still starting off with oxidation numbers so that we can determine what's oxidized and what's reduced. The difference here is instead of just finding a multiplier, I'm going to pull apart my half reactions. I want to balance those using the same steps that we just did, yes, including water and hydrogen as necessary. And then we want to find out how many electrons were involved in each change. For the oxidation, since we're talking about loss, the electrons would be present as products. Whereas for reduction, where we're talking about gain, the electrons would be reactants. And we're going to put those into the equation, similar to how we put heat into the equation, by just writing them in as reactants or products. Then we want to see if they're the same. If they're not the same, you may have to multiply an entire reaction by a coefficient in order to get the electrons to be the same. You may have to do that to both equations. The goal is to get the same number of electrons being produced as you have being reacted. Once you have that, you want to cancel out things that are the same on both sides and write your net reaction when you combine it back together. So let's give this a shot. again with oxidation numbers first. So here I have hydrogen of +1 and oxygen of -2. So I have a -6 and a +1. I'm going to need a +5 on that nitrogen. Hydrogen +1, sulfur -2 then. Oxygen's -2, so the nitrogen will be +2 by itself. So we've got a 0, and then +1 and -2. So what's my change? I see a +5 on the nitrogen to a -2. So going from +5 down to +2 would be a decrease of 3. And then it's the sulfur, that's the other change. Going from -2 up to 0 would be a gain in 2. Yeah. So you can see how those are different. This is our entire problem. Now, we have to identify which one's oxidation, which one's reduction, so that we can put the electrons on the right side. The negative is always the reduction. Reduction is gain. I've gained more electrons, decreasing my oxidation number. Whereas the positive would be the oxidation. Oxidation is a loss. Losing electrons makes it more positive. So I'm going to write the oxidation half reaction first so that I can show the electrons being an intermediate, having them be produced and then used up in the reduction. So to write the oxidation half reaction, I am only going to focus on the parts of the problem that are attached to the oxidation bracket. So I'm going to write this as H2S forms S, and I'm going to ignore everything else in the equation. First thing I'm going to check for is that oxygen problem. I do not see an oxygen problem. As a matter of fact, there's just no oxygen in this part. But I do have a hydrogen problem. Since I have 2 hydrogens on the left, I'm going to need to bring some hydrogens in on the right, and that'll always be brought in as ions. I have 2 of them here, so I'm going to need 2 of them there. So we're bringing in the hydrogens to balance. When you add water, you always have to add the hydrogens to fix it, but it is also okay just to bring in the hydrogens like this to fix an existing problem. So now I have a balanced reaction as it is at the moment, the half reaction as far as atoms go. But let's talk about the electrons. Oxidation is loss, so I'm losing electrons. The number of electrons will depend on the change in oxidation number. This +2 represents that each sulfur atom has a change of 2 electrons. If I had twice as many sulfur atoms involved, I would use twice as many electrons. So be careful for that. Okay, so that's my half oxidation reaction. Now let's write the half reduction reaction, looking only at the things that are connected to that reduction bracket. So this is going to show my nitric acid, HNO3, breaking down to become NO. So I want to balance the reaction first, looking at my oxygens. So I have 3 oxygens here where I only have 1 here. Product having less oxygens means I'm going to need to add water. The catch is how much water. I want 3 total oxygen atoms, but I do already have 1. So I'm only going to bring in 2 water molecules. Now that creates 4 hydrogen, where I already had 1 over here. That means I'm going to need 3 more. So 3H plus on the left-hand side. Let me move this over a little bit. So now I've balanced my oxygens, my hydrogens, my nitrogens already were balanced. Now I want to think about the electrons. So with the nitrogen, each nitrogen had a change of 3, and it's reduction, so it's gain. So those electrons are on the reactant side. Now, is it possible to lose 2 electrons, but yet gain 3 electrons? No, that's the whole point here, is that the gain has to equal the loss. So what could I gain and lose? What could I multiply each of these up to? 6, which means I'm going to take my first equation and multiply it by 3, and my second equation and multiply it by 2. So I have 3 H2S, 3S, and 6 hydrogens, and 6 electrons. Once I write the multiplied version, I like to cross out the original version. Just prevents confusion, right? Now let's go 2 across the entire bottom equation. So it's going to be 6 electrons, 6 hydrogen ions, 2 nitric acids, 2NO, and 2 times 2 here, 4H2O. Cross that one out. So I'm only looking at the multiplied equations to compare them. Actually, let me go ahead and erase my original equations so it's a little more clear. There we go. So now that we have multiplied each of our equations up to give the producing 6 electrons and using 6 electrons, it's time to combine them. And just like we did with like Hess's law or net ionic equations, anything that's on the product side and reactant side will cancel. Your electrons better cancel at this point. That was the entire point of multiplying the equations. Something else cancels in this example. I have 6 hydrogens on the left and 6 hydrogens on the right. So that will also cancel completely. It's also okay for things to cancel partially. For example, if I had 4 hydrogens versus 6, that would leave me with 2 on this side. This time it cancels completely. So now I want to put these two equations together. So my reactants are the 3H2S and the 2HNO3. And it doesn't matter which one comes first, those are your reactants. And then my products were the 3 sulfurs, the 2 nitrogen monoxide, and the 4 waters. And again, the order is unimportant, but you want to include all 3 products. And that will be my final balanced reaction using the half reaction method, where you pull apart the equations in order to solve them. All right, so oxidation numbers first. Figure out what's the oxidation, what's the reduction. The electrons are produced in the oxidation and used up in the reduction. All right, let's do one last one. And in this one, we're going to walk through how to make it appropriate for an acidic solution. Then we'll take that answer and go ahead and turn it into the basic solution. This will give us practice with both methods. So we always start with our oxidation numbers. So the oxygen -2, this will be -6, and I want a -1 left over. So the chlorine this time will be a +5. The bromine -1, chlorine -1, and bromine diatomic would be 0. So my change is from the chlorine of +5 to -1. So that would be a drop of 6. And then the bromine goes from -1 to 0. That would be an increase of 1. So the drop is always the reduction, and the positive is always the oxidation. And I'm going to start with the oxidation half reaction first. I always do oxidation first, so it always shows producing electrons and then using them. So just pulling out the bromines, I just have bromine ion producing a bromine molecule. Now that can't happen. 1 bromine ion producing 2 atoms, so it would need 2 ions in order to produce this molecule. And that balances the bromines. Now let's think electrons. This is oxidation, so it's going to be a loss of electrons. And each of the bromines has a change of 1. But how many bromines are included? 2 of them. So I'm going to double my number of electrons. That's the tricky part. This is the change per atom. Since I have 2 atoms, I have twice the electrons. Now let's look at the reduction reaction. So the reduction is ClO3 minus producing the chlorine. So 1 chlorine on either side. Now let's address the oxygen problem. So because I have oxygen on the reactant side but none on the product side, I must bring in water in order to balance the oxygens, which I had 3 oxygens, so I'm going to need 3 waters. Now I have 6 hydrogens, so I'm going to fix that on this side by adding 6 hydrogen ions. That's going to balance all my atoms. Now let's think about the electrons. Here it shows I had a change of 6 per chlorine, and it's only 1 chlorine this time. So I'm going to have 6 electrons. Now I can't use 6 electrons when I've only given off 2. So this top equation is going to need to be multiplied by 3 to get to 6 electrons. So 3 times 2 is 6 bromine ions. producing 3 bromine molecules and 6 electrons. And that'll do it for the top equation. In this case, only the electrons cancel, so now I can start combining everything. So I have my 6 hydrogen ions and the ClO3 minus and my 6 bromine ions, producing those 3 bromine molecules, the chlorine ions, and 3 waters. This combined reaction would be the finished answer for my acidic solution. Got my chlorine or my hydrogen ions here. Now, to make it basic, I would have to go through all of this stuff anyway. Now, at this point, I would start doing something a little bit different. I want to neutralize 6 hydrogen ions. So I'm going to add, oops, I don't know why I put a plus in front of that. Let me clean this up. So I'm going to take 6 hydroxide ions and add them into either side. So that's also going to get added to the product side. When you add hydroxides, you add both sides evenly, and the number is determined by neutralizing the hydrogen. So speaking of neutralizing the hydrogen, that's going to now combine to form 6 water molecules. But you have to be careful because there's usually water on the other side. So there's 3 waters on the other side, so I'm going to cancel out 3 of my 6 waters. So my final answer as a base would have the 3H2O on the left, and then this middle part would be the same. I've got the ClO3 minus, the 6Br minus, making 3Br2, oops, lost the 2, plus Cl minus, and then the water's gone, and now I have the 6 hydroxides on the product side. So this would be converting to having it as a base for the final answer. So you want to be careful whether you're in an acidic or basic solution. Recombine them, and then if you have the hydrogens and want to make it a base, then you use those hydroxides and just watch for canceling your water. All right. So I just wanted to end with this nice and typed up so you can see the final answers as an acid and a base for for balancing this redox reaction. That's going to do it for balancing redox, guys. Next set of notes is Unit 12, Notes C, where we're going to discuss electrochem. We'll see you there.